Right. So the last day we started looking at our wind turbine, and we got a certain distance in that. So this was it really. As you can see, it's a lot simpler than a house, but you know, at the same time you need to be careful in terms of how you put it together. So we're reading in our wind speeds from the workspace. We generate the polynomial coefficients to convert wind speeds into megawatts. So we're given the power curve here, and we need to convert wind speeds into megawatts. Let's say this was 10 megawatts, 100% might be for a wind farm. Remember, a wind turbine is typically, well, the biggest ones are about 6. But if you could have 5 2-megawatt wind turbines in a small little wind farm. So the maximum output would be 10 megawatts. Okay. So it looks simple, but there's a fair bit of work behind it, because remember, you need to have the power curve defined, and that's done in a script. So we're reading off the power values according to certain wind speeds. So there's our curve, and we have no power output for the first X. It's not much good either. I don't know. So in our case, our wind farm has a maximum output of about 10 megawatts. And that's reached at about 16 or 17 meters per second. So up until the first 0, 1, 2, 3, 4. At around 4 meters per second, we start to lift off the axis. And as you can see, we're developing 0.4 of a megawatt. Then we have 5, 6, 7, all the way up. So what we want to do first of all is extract the coefficients, the 5th order coefficients for that power curve. And then it's specified in this variable here, P coefficient 5, and that's what we specify in our model. If you double click on that, what you get is this here. Alright? So that when you run the model, you have a variable set there which is specified in your curve, or in your script. Okay? Now in this case, I am not running the script from within the model workspace. The script is just running as a script, puts the data in the base workspace, and of course the model, if it doesn't find the values in the model workspace, it goes and looks for them in the base workspace, which is what's happening here. Okay, what else do I want to say about that? Yeah, I just thought maybe this morning I might just go through the workspace, because there's quite a lot of data in there, and it relates to quite a lot of things. So when you run the script, you've got m and n. So m and n is the size of this vector, right? So remember, this is where I'm reading the data off the power curve. So you're literally eyeballing the curve and taking values off it for every meter per second wind speed. So here's your speed data, which is the x-axis, and here's your power that I'm reading off the curve on the y-axis. Okay? So that's why you get those values in the workspace. There's power, 20 by 1. M and n is 20 by 1. And speed data is 0 to 19. Okay? So 0 to 19 meters per second. And that's here, there's speed data there. Alright? So when you run through that, we generate the P coefficients, the 5th order P coefficients using polyfit, give it the speed data and the power, specify 5, and there's the coefficients there. What else do we have? Right. This part of the script is just recreating this curve. Now, I just did that to show you the curve. There wasn't a necessity to do this for the model. The model will run fine. This is just showing you the fit between the actual data and the fifth order data. So that's all done here. That's where S fit comes from. That's where that vector comes from. So you can see S fit and Y fifth order. Here's S fit. Why is it 96? It's 96 because we're going up in steps of 0.2. So we get a nice smooth curve. And then we have Y fifth order, right? So 96 by 1. Okay, finally, we have the name of the file for the wind speed. So we have now got the characteristic for the wind turbine. Now we want to actually read in the data for actual wind speeds, and let's see how many megawatt hours we generate over that one day, right? So we read in the data. It's 1 day's wind speed. It's in minutes. We know that because there it is up there. Okay, so here's the timestamp in minutes, and there's the wind speed at that minute. So this model will run every minute. Sorry, this model, the time units are specified in minutes. How often the Simulink model runs depends on the parameters, as you know. Simulink decides itself how often it will run in terms of iterations, but it will run for a period. The data is being read in minutes. Okay. So the size of data. So this is the Excel spreadsheet. You can see it's got text, because this is text really, it's not data as you can see, because it's got these dates in it. This is the actual data. So there's the data being 1440 by 1. So if you look at 24 hours by 60 minutes, you find it's 1440. So it has a value for every minute of that day. So P and Q should be 1440 by 1. Here's P and there's Q, 1440 by 1. Alright? And then the time vector is from 1 to P. In fact, the time vector should really start at 0. I don't know why I started it at 1, but it won't really matter that much. So T is the time vector we're going to use for reading in per minute the wind speeds. So we're ready to run the model once we run that script, because in other words all the data is needed. So as you saw the last time, when you run that model, this is what you get. Remember to put in your viewers. These are the scopes there, because they allow you to see exactly what's going on. Otherwise all you see is what's out here. So if you want to see what's happening at each point in your model as it runs, put in those scopes. Okay? Yeah?
The data reading, when you put data on text 2, what's the text 2 for?
It's just to get rid of, it's in other words, it creates another, see it here. Here it is here. It just, so what it does is, so if it, yeah. It's essentially, when it can't read it as a number, it just dumps into this structure called text. Right? Generally of no use to you, but it may be of use to you. It depends on the formatting of the Excel spreadsheet. I mean, I know some of you, as I mentioned, have been using the auto-generate code, which is a real mess because it's just absolute. It might work, but try and make sense of it. So use that very simple, right, way of reading in data from an Excel spreadsheet. Okay? So the interesting thing here is that day, whatever day it was, in December 2010, we had very low wind speeds. So as you can see, the wind speeds rarely got just to 3-point-something meters per second. So essentially we're down here all day. So it wasn't a very good day for generating power from your wind turbine. However, the problem is, because we did a fifth order fit, as I said the last day, the green curve, which is the fit, dips below 0. And in fact, much of the wind speed is in this area here. So in fact, if you were to use the fifth order polynomial as it exists, you're generating negative megawatts. So that's why the power limiter is a very useful contribution or addition to the model. Like, you need it. You need this power limiter. Okay, you need it for two reasons. You need it for down here, and you also need it for maxing out at 10 megawatts. Okay, so as you can see, the output from the polynomial is actually negative a lot of the times, because we're generating negative megawatts, except for a tiny spike at this point here, where we just about generate a very small amount of megawatts. So as you can see, the y-axis here is tiny. So we actually only generate one spike of megawatts during the whole day. And because you're integrating, the value jumps and then stays fixed for the rest of the day. Alright? So not a very good day for generating wind power. So, what I did was I just multiplied the wind speeds by 3, just to see what happens. So you can see here, I manufactured this kind of data. And of course now we have wind speeds that are reasonable. So as you can see, we hit about 10 meters per second. So we're well up in the power curve now. So we actually are generating some megawatts. Therefore we are generating megawatt hours. So as you can see, this is the limiter output, and this is the polynomial output, but they're the same. In other words, we never dip below 3 meters per second. Therefore, we never get into these negative values down here. So the limiter really at the bottom end, or the top end, doesn't serve much of a purpose there. And we get some nice megawatt hours. So here I scale it up again. So as you can see, this is 10 times. So we have a hurricane. We have a very windy day, maybe like we had in a few weeks ago, or less than a few weeks ago. In fact, for the last 2 months, almost. So you can see a very, very windy day in terms of meters per second. Remember, go back to our scale here at the very start. This is meters per second. So anything above 20, you're talking about storm force 9. Strong gale. Remember, we got up to hurricanes down in the south 2 weeks ago. So we're generating loads of megawatts. Yeah. So, now, the interesting thing here is that, remember that we max out here at around 16 or 17 megawatts? Right? Or 16 or 17 meters per second. We max out at about 10. And the polynomial, if we look at it here, you can see this, the green one. It dips there, which again is another modelling error. Well, what can you do? You could go higher order maybe, get rid of that. But you see the way the curve is going here? It's starting to increase. So that's why, if you look at the output here, the limiter, the red one, is right down here at the bottom. Now, it looks a bit strange, but if you look at the y-axis, we're talking 400 megawatts here. Right? So you can see that the output of the polynomial, here is going up into the hundreds of megawatts. So the power limiter brings it back down to 10, because the wind farm has a maximum output of 10 megawatts. So I know it looks a bit misleading here, but this is actually 10 megawatts. So we actually have peaked out on the wind farm. And these huge values are caused by essentially that third order, that fifth order polynomial curve. And just to show you that, what I've done here is, okay, I generate my P coefficients 5 in that script, and then I replot the curve, but I extend it beyond 16 or 17, or beyond 20 meters per second. And as you can see, beyond 20 meters per second, that curve takes off to the sky. So that's why, like this part of the curve here, what you see there is essentially what you see here. It's just that I'm now plotting it out to 25, but because the trend is up in that direction, what you see essentially is this. So that's what's causing the error there that we need to make sure we take out using the limiter, which is what we do there. So that's the value of Simulink. You know, you can very quickly model the real system by putting in these limiter blocks. Okay. Right, so just to summarize in terms of units, so we're reading in the wind speeds every minute, generating megawatts, but remember it's every minute. So when we're converting from megawatts to joules, megawatts to a megawatt, remember, is a megajoule per second. And mega is 10 to the 6. So multiplied by 10 to the 6. But because our time units are minutes and not seconds, we need to multiply by 60. So multiply by 60 to convert from seconds to minutes. So we go from megajoules per second to joules per second, and from joules per second to joules per minute. So the million is converting from megajoules to joules, and the 60 is converting from joules per second to joules per minute. Integrated per minute, and then converting back to megawatt hours. So data read in minutes. Okay, the second model, and actually I'll put this one up on Blackboard when I go back, so you can run this model yourselves. Okay, the wind turbine one. Okay, tidal turbines. So much the same idea. They're starting to be commercially deployed now. There's a company called, in fact, I think one of you guys did your placement. Is he here? Open Hydro. One of this class did one of your third years. Sorry, yeah. One of the current fourth years did his placement with Open Hydro. Anyone have heard of Open Hydro? They're in County Louth. They make these tidal turbines. They didn't make this one, but this one has been in Stratford Lock for the last 5 or 6 years now. And that's it with the turbine blades lifted out of the water for maintenance. So it has a blade diameter of 16 meters. So it has two blades. Well, you can't really see it. There's another blade at the far side, and they go down to the water. 16 meters is about 50 feet in terms of a blade diameter. You can see the power curve is quite similar to a wind turbine, and it's the same idea. What's the relationship between power and velocity? Huge. It's the very same in terms of the relationship between how much energy can you get out of wind blowing at X meters per second, how much energy can you get out of water flowing at X meters per second. It depends on... Huh? How fast will the water flow? Well, you can see there Stanford Lock. If you consider in a hurricane, you've got wind speeds of 25 meters per second. Here we have at the maximum tide. So I don't know, I know I've asked this question before, who's into fishing here? Who knows the tides? The maximum tidal current is mid-tide. So again, it's like a sinusoid, the tide. So there's your meters per second over time. That's your typical tide. It depends on the physical characteristics of the tide, but at these points here, the current. So, the tide starts to comes in really quickly, then starts to slow down, reaches the highest tide, and then slowly starts to go back out again. really quickly, it starts to slow down again. So it's essentially this curve here. In some parts of the world, you get tidal currents up to 10 meters per second. Now, if you can imagine swimming, even here actually, if you look out here on the river, I mean, what speed do you think the current is at the moment? Anyone here rowing? Have we any surfers here? Very few people here. Anyway. Have we any surfers? No. No surfers, no rowers. What do you do to do the exercise? Huh? Okay. Well, okay. The IT guys, when you're walking down to the IT building after this lecture, have a look. Take a spot point in the water and measure it over a second. How fast do you think the current is out there?
2 meters. 10
About 1 meter per second.
If you were to try, 10 would, 10 is in fact 10 is so bad that they've tried to put these turbines in Canada and they can't find them after a week, and they're found. They're found somewhere. It's very hard to build something that will survive 10 meters per second. It's shocking. It's shocking energy. Remember, the energy is proportional to the density. So a tidal turbine has a huge advantage in that water has density 1,000 times higher than air. So in terms of how much energy you get out of a tidal turbine, it's literally the relationship is 1,000 between wind and, in fact I show it there, between wind and tide. The formula is identical. Absolutely identical. If you didn't already notice that. They look a bit different here. I mean, what's the area of a circle? What's the swept area of a turbine? Pi r squared, which is pi d squared over 4. So pi d squared over 4 is the same as A here, right? Velocity cubed, velocity cubed. Density, density. And then you have your efficiency factor, which is a squiggle, right? And remember, it's about 0.6 for wind. It depends on the turbine. So that's where they're trying to get their energy gains all the time, improve the efficiency. So it's all about kinetic energy. It's a half mv squared, really. That's the theoretical maximum you can get. How much you extract depends on your turbine. But the density is the key difference here. Okay, so here's our tidal turbine model, which looks very similar, needless to say. So instead of reading in meters per second in terms of wind speed, what I have here is I'm modeling the tidal flow. Because remember, the tide goes in, the tide goes out, the tide goes in, the tide goes out. The cycle is about 12 hours. It depends. It's 12 hours and something else. On average, I think the tide is 48 minutes later every day. So if we have full tide at 9 o'clock this morning, full tide tomorrow will be at about 9:45. Again, it varies depending on lots of little things. But on average, the tide is about 48 minutes later every day. So it's not quite 12 hours, but 12 hours, in other words, there's 2 tides per day, but 12 hours is a rough approximation. So here's our meters per second coming in. We're converting it to megawatts, but we need an inverter. Why? Because we're getting power on both the way in and the way out. Right? So if I jump straight to the output, you can see here is our tide and current. Tide coming in. Right? So you can see the velocity changes direction. Right? So the tide starts to go out. So that's what the inverter here does. So you get the... However, you can see here that the curve isn't actually identical, but we're ignoring the differences between the ebb and the flood in terms of the efficiency. That's the physical characteristic. You don't get quite the same efficiency on the ebb as you do on the flood. Which is the tide coming in?
Flood.
Flood, and ebb on the way out, okay? Alright, other than that, it's much the same. We have to derive the power curve for that polynomial, or for that turbine. So essentially we take the points off the curve, and that's done here. Alright, so I'm taking the points off, and I'm generating the coefficients. For the fun of it, I'm generating the coefficients using the first principles there. So using general linear regression. Right? So in the exam you could be asked to just use polyfish, in which case you just put in a one-liner. There's the one-liner there. It extracts the coefficients for you using the polyfit function once you give it the relationship between speed and power and the order you're looking for. If you're asked to develop it from first principles, you have to put in a few more lines of code that shows that you can do that, which is just this here. So you're extracting the coefficients by giving it the power, and you have to create this matrix yourself. You know the one that ends in the whole column of ones? Or in other words, to the power of 0. So what you're saying is the power output is the speed j to the power of 5, the speed j to the power of 4, speed j to the power of 3, speed j to the power of 2, the power of 1 to the power of 0, which is just 1. Alright, but ultimately what you're doing is you're generating the polynomial coefficients. Okay, so we now have the polynomial coefficients, and then we convert back to joules, integrate it, and convert it back. So this is what we get. Here's our 12 hours converted to seconds. Right? So in other words, what we're saying is we're going to run this model, the time unit is seconds. 90,000 seconds is approximately what? A day. Right? That's 86,000 seconds in a day. That's approximately a day. So this is what you get. Alright? So if that's the Stanford lock, which it is, power curve, so 1200 kilowatts is how many megawatts? Sorry? 1.2. So in other words, the Stanford lock device, which has been in operation and actually producing power for a couple of years, is 1.2 megawatts, 16 meters squared. A 1.2 megawatt wind turbine is like the ones out in Spindle. A hell of a lot more than 16 meters squared. But then again, that's because you're using air rather than water. Okay. So here's our current, here's our absolute current, there's the megawatts being generated, and this is the integral of the megawatt hours, and that's converted to joules. Remember, a megawatt hour is a unit of energy. A megawatt hour is a megajoule per second multiplied by the number of seconds in an hour. So that's why the y-axis here for joules is a hell of a lot more than the y-axis here, which is megawatt hours. But again, engineers tend to talk in megawatt hours or kilowatt hours rather than joules because it's such a small unit, the joule. Okay, so that was running the model in seconds, right? So our time unit is 90,000 seconds. You could just run it in minutes. So here's our tidal current, 12 hours multiplied by 60. But if you specify your input in terms of your time unit in terms of minutes, then you need to make sure you have minutes here as well. So instead of 90,000 seconds, I have 24 hours multiplied by 60 minutes. And similarly here, I have to multiply by 60 to convert from joules per second to joules per minute. So just, again, make sure you get your units correct. Okay, that is the same. Okay, folks, we leave it at that.